Alright, continuing with ME627. Today we are doing Introduction to Averaging. The method of averaging it's a perturbation method, and you will see what it does, but let me tell you quickly. With Poincare-Lindstedt we found periodic solutions. We did not get transients, we did not get the stability of the solution, we did not get aperiodic solutions, we got none of those things. But in vibrations, we may have vibrations where something has a growing amplitude, there is an amplitude envelope that we may be interested in capturing. We have seen the van der Pol oscillator, it has an amplitude that increases and approaches a limit cycle. Such things, only the steady solution is possible to be captured with Poincare-Lindstedt. But with method of averaging, we can get the transients, we can get stability, we can get aperiodic solutions, for example damping or things like that, effects. So maybe the amplitude goes like this, and we want to understand how fast the amplitude goes to zero, and we can get such things with the method of averaging. But to understand the method of averaging, we have to take an easy problem first. So here is an easy problem, first order scalar system. X dot equals minus epsilon x sine squared t plus x, and epsilon is a small number. Now this system, you see, it's not separable. You can't solve it analytically. However, we can look at numerical solutions, and the point is, the idea is that because epsilon is small, you see, because this epsilon is small, x changes slowly. Because x changes slowly, this oscillatory part, it's almost like a constant phase, and it's like sine square t, its average value is half. So the question is this a reasonable approximation? Is it? So we will check that first, and then we will talk about it. Where did this half come from again? Let me say average of sine square t plus x is about half. Why? Because x changes slowly, so over here it's nearly a constant. That's the thinking. Okay, so we will come back to this drawing sheet. Let us go to MATLAB here, and let me just clear things. OP equals, let me specify that. Here is the differential equation. That epsilon I've chosen a small number, 0.04. X dot is minus epsilon x sine squared t plus x. Okay, save. We come here and I look for this. Let me use a time period, a time duration of 50. Let the initial value of x be 2. Okay, here's the solution. Well, I called it y, so you see that it is oscillating but going down on average. Okay, I can run it for a slightly longer time, maybe 150. And you see that it was oscillating and it has gone down. And what I had suggested is that we may like to compare it with 2 times e to the power minus 0.04 times t by 2. And plot that in red. And you will see that the match is essentially perfect. Okay, so the red is what we will call the averaged solution, and what it has done is it has captured the mean variation and thrown out the oscillatory part. And you will agree that this is not a bad thing to be able to do. And so let us go back now to the drawing and try to formalize this. Okay, so we will come here, and to apply averaging, the system must be put in something called Lagrange standard form, which is this: x dot equals epsilon some function of x and t. X can be a vector. Okay, so x can be a column matrix, for example. That's okay. All right, so this is our original system. What is the approximating system? So there is a periodic case. The periodic case is f of x t plus capital T is equal to f of x t for some t greater than 0 and all x, all t. Okay, so this is periodic. In this periodic case, it is simplest. Okay, so in the periodic case, what happens is we define f a of x to be equal to the average over one cycle of t plus capital T of f of x t dt, with the understanding that this one is treated as constant. Okay, so when we do that, this becomes a function of x only, right? Because the t was a dummy variable of integration over here, and then we say x a dot is equal to epsilon f a of x a approximates that. This is called the averaged system, also called averaged slow flow. Okay, why slow? Because it is slow, the time dependence is gone, no t, so it just gives you the average. Okay, so if we go back to our system here, we have to see sine squared t plus x. What is the period? T is actually equal to pi, because this is second harmonic, but you can take it as 2 pi also, it doesn't matter, or 2 pi if you wish, it's okay. And then x is just treated as constant. So what happens is f a of x is equal to 1 by 2 pi integral 0 to 2 pi x sine squared t plus x dt with x treated as constant, and that gives us x by 2. That all of that is now replaced by this, and so our averaged slow flow is x a dot equals minus epsilon xa by 2. Okay, and then the solution for that is e to the power minus epsilon t by 2 times whatever the initial value was, and that is what we have been plotting here. Okay, the 0.04 is not special, so over here I can make it 0.01, and if I do that, then maybe I will extend this to 500, and then this just has to be 0.01, and you will see just very good indeed. Why? Because this is an asymptotic method, right? In fact, the variation is smaller. Okay, now how good is it? How good is it? So, and how long does it work? So to understand that, we have to understand why averaging is so nice, you know. So to let's come here and pretend that we didn't know averaging. So suppose we try a regular perturbation expansion. How will it do? So here we have x dot is equal to minus epsilon x sine squared t plus x. We will try x is equal to x0 plus epsilon x1 plus something. We will substitute it there. We will have x0 dot plus epsilon x1 dot plus dot 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 is equal to minus epsilon x0 sine square t plus x0 plus order epsilon square. I hope you see that that is what it has to be. Therefore x0 dot is equal to 1, sorry, 0. That means x0 is a constant, and then x1 dot is equal to minus epsilon x0 sine square t plus x0. And now this side is independent of x1, and so x1 is just going to have some wiggles, but it will have an average linear growth rate. You see, because this has an average value, x0, average value of minus epsilon x0 by 2 on average, right? And so x0 is going to be a constant, and x1 is going to be, whatever you do, it will be some straight line like this, right? And you may give it an initial condition of 0, in which case it will be this one, and then whatever happens, basically it will break down. When will it break down? This has a linear part which is like t, so it will break down when epsilon t is comparable to 1. That means t is order 1 by epsilon, big O. Okay, that is what we don't want. We want it to be t, it breaks down, right? I mean, so regular perturbation breaks down on this time scale, yet that is the time scale of interest. In comparison, when we do averaging, so when we do x a dot is equal to epsilon fa of xa, then we say that xa0 will be equal to x of 0 plus some small thing only, and then there will be such an initial condition such that xa of t will be equal to x of t plus something of order epsilon on time scales of t equals order 1 by epsilon. So this is actually a huge advantage. You are able to see how things change. If you read the formal theorems, for example in Verhulst, what they will tell you is, in addition, if x of t has a hyperbolic stable solution, then xa approximates x for all time. I mean, if xa has and approaches. Okay, so there are situations where it is not just this 1 over epsilon, but actually infinity. But this is a useful guarantee. This is what we do, what we use. Okay, now what happens if we have other problems? So for example, what I want to do, let us try this simple example, x double dot plus epsilon x dot plus x equals 0. We know it's exponentially damped. It doesn't have a periodic solution. In fact, if you try Poincare-Lindstedt, you will find that you are getting you are forced to conclude that the amplitude is 0, because that is the only periodic solution it will allow. However, we can think of averaging here, except it is not in Lagrange standard form, right? So because it is not in Lagrange standard form, we have to do a change of variables. This change of variables is done on the first order system. Okay, so we will write it like this. We will say x dot is equal to v dot is equal to minus x minus epsilon v. This is our first order system. And then what is a good change of variables? We will be guided by epsilon equals 0 system. This is a critically important idea. Okay, that is for choosing change of variables. But first let us see what is the arithmetic for a change of variables. See, I can say let's see, I can say x is equal to u sine t plus v, and I can say this is not a good idea. I have a v here and I have a v here, so let me say w, u and w, and I say v is equal to w plus u cos t. See, this is a legitimate change of variables. It's just not a very useful change of variables, right? If I was making this change of variables, then what I would have to do now is I would have to say x dot is equal to u dot sine t plus w plus u cos t plus w times 1 plus w dot, and I would have to say v dot is equal to w dot plus u dot cos t minus u sine t. And then what I would do is, what I would have to do is I would take this and put it here, and I would take this and put it here, and I would take this and put it for v dot, and I would take this and put it here, and this one and put it here, and then I will have a new system of differential equations for u dot and w dot in terms of u, w and t. This is perfectly legitimate. But useless. It doesn't help us. What we can do is a better change of variables. And for that I have to find. What we can do is a better change of variables. So what we do is, we notice that for epsilon equals 0, x double dot plus x equals 0, x is equal to a cos t plus phi is a solution, with a x dot is equal to minus a sine t plus phi is a solution. A and b are constants. This is for epsilon equals 0. For epsilon not equal to 0, we can use this as a change of coordinates, only we let a and b be time varying. It is a perfectly legitimate change of coordinates. Okay, so this is actually a classical method called variation of parameters. Okay, and so the way we will do it is in a slightly general way. We will say x double dot plus x is equal to epsilon some function of x dot. For the moment, let us do that. We can have t also. There are some issues there, but let's put it. Why not? Doesn't matter. Okay, so this is our system. But what we will do is we will write it as v dot is equal to minus x plus epsilon f, and x dot is equal to v. This is our system with this change of coordinates. Okay, so I think I'll need a new sheet. Let me take that, and then we will begin. So file, new, no. Okay, so that's nice and big. Okay, so here we go. So we have v dot equals minus x plus epsilon f of x v t, and x dot is equal to v. Meanwhile, I have x is equal excuse me, x is equal to a cos t plus phi. X dot is equal, no, that's not good. I will write it as v is equal to minus a sine t plus phi. Okay, following what we were doing earlier in the other example, I will first differentiate this. I will say x dot is equal to a dot cos t plus phi minus a sine t plus phi times 1 plus phi dot. Okay, this thing has to be inserted here, and this thing has to be inserted here. Okay, what does it give us? It gives us a dot c, I'm writing c for cos t plus phi, minus as phi dot is equal to minus as, because this v is minus as, or a dot c minus as phi dot equals 0. This is one differential equation. This is the one that we got from this change of coordinates and this equation. Okay, now we'll do the other one. So we'll come here. Let me use green for this. V dot is equal to minus AS minus AC 1 plus phi dot. So I'll come here and put that, and you'll see I'll put minus AS minus AC phi dot is equal to minus X, that's minus AC. I think I've made a mistake here. V dot is equal to minus A dot S. Okay, so minus AC, that's X, plus epsilon F. It is understood that inside F I am going to be substituting whatever there was. Okay, so now just like this had cancelled here, it is not an accident that this will cancel here, and I will get my second equation, which is A dot S plus AC phi dot equals minus epsilon F. Okay, very good. Now I will have to, I think it is better if I scroll down like this. So let me now multiply the first equation with C and the second equation with S and add it up. Then I will get A dot is equal to minus epsilon F sine t plus phi, and F has a dependence on xx dot t, right, x, b and t, so we will put that in, not to worry. And then what I will do is I will multiply this one with S, this one with C, and subtract. Okay, and then what will happen is those will cancel, and I will have minus A phi dot. I'm multiplying this by S, this by C, and subtracting. So I'll have minus AS square minus AC square, so S square C square. So minus A phi dot is equal to epsilon F cos t plus phi, or phi dot is equal to minus epsilon F by A cos t plus phi. Okay, and let me erase this. And you can see that this system now, put it in yellow, this system is in Lagrange standard form. The key idea is for epsilon equals 0, find general solution with arbitrary constants. Now let those constants be variables for epsilon not equal to 0. That's the idea. It'll always work. Okay, good. Let us do this for the damped oscillator. Okay, so here we are. I'm doing this one now. I'm doing x double dot plus x equals minus epsilon x dot. That means f is equal to minus epsilon x dot is minus, f is equal to minus x dot, which is the same as minus v, right? Very good. We come here and I find A dot is equal to minus epsilon fs. Very good. So I come here, I get A dot is equal to minus epsilon fs is equal to this minus and this minus will cancel, so I'll have epsilon. then I'll have V, and the V is minus AS. So I have minus AS, and this is another S, so that's S square. Alright, very good. And then what do I have here? I have phi dot is equal to minus epsilon FC by A. So I come here and I have phi dot is equal to minus epsilon FC by A, and that is then going to be minus epsilon ASC by A. This A will cancel, and so my system in Lagrange standard form is A dot is equal to minus epsilon A sine square t plus phi, and phi dot is equal to minus epsilon sine t plus phi cos t plus phi. Okay, then you do the averaging, you get A dot is equal to minus epsilon A by 2, phi dot equals 0. In fact, if you look at the exact solution for that problem, then the exact solution is if I remember correctly, is some constant. The exact solution is some constant e to the power minus epsilon t by 2, and then the sine of the square root of 1 minus epsilon square by 4 times t plus some phi naught. That's the general solution for that. And what happens is, this constant is not important. When you expand this in a Taylor series, you get order epsilon squared, you see, and that is how the phase slowly changes. And this is actually order epsilon square if you do higher order averaging, which we are not doing today, but we will do it later. So from first order averaging, this is what we can get. That's all for this lecture.